Last time I talked about that relationship between traction on a face with a known orientation and stress. Remember that? Oh, wait. Yes, that's going. Okay, so so the relationship between the stress tensor and the traction on a face. With a known orientation. And that relationship was the traction vector is equal to the stress tensor times the outward facing normal. Where'd all my toolbars go? Okay, so this is the outward facing normal. You could use that two ways. If you know the stress tensor and you don't know what loads are acting on an external surface, you could do it that way. So, like for example, let's say we have a surface like this. So that's some material. The coordinate system is like this. This angle is 20 degrees. And let's say there's a distributed load on this face. And we know that at points on the surface, the stress tensor is 6, 0, negative 5. I'm just making these up. But it does have to be symmetric. So 0, negative 15, 2, negative 5, 2, 2. And these are in megapascals. What's the traction vector for points on that face? Well, we have to come up with an outward facing normal vector. So I'm going to, in order to figure that out, this is something the people who took statics with me, like, this is sort of how I always think through like angles and stuff. But to come up with an outward facing normal there, I know it's 20 degrees from the positive x-axis to here, so I'll draw a vector there. And that's counterclockwise from the x-axis, so that's going to be positive. And then the outward facing normal is perpendicular to that. Whoa, that was almost hilarious. Not for me. I don't think. Yeah, that's true. And then 90 degrees clockwise from the blue to the red. And so the angle, the counterclockwise angle from the positive x-axis is 20 to get to the blue, minus 90 to get to the red, and so theta is equal to minus 70. And so that outward facing normal is cosine of negative 70, sine of negative 70, 0. And that is 0.342, negative 0.9400. So now that we have the outward facing normal, we have this stress tensor, so the traction on that face is equal to 6, 0, negative 5, 0, negative 15, 2, negative 5, 2, 2, times the vector 0.342, negative 0.940, 0. And anybody, can someone punch that into a calculator or hand me a calculator? 2.052, 14.1, negative 3.590. I love the significant figures. That's the way to get in the spirit with the random significant figures. Megapascals. Okay, so based on the stress tensor at those points, we know the distributed load vector acting on those points of that face. More often you go the other way, so this is an example of the way you usually use it, and we're not going to have to do this in this class, although this relationship between tractions and the stress tensor is going to be important. But if you're doing like continuum mechanics, hand calculations of stresses and strains, usually the boundary conditions you have are, you know what the loading is at a surface, like you know the distributed loads acting on a surface, and you're trying to calculate the stresses. So let's say there's the object, and we're going to use that same standard coordinate system orientation. And let's say that we know that on this face, there's a distributed load going that way of 20 megapascals. You could think of that as like a pressure acting on it. And there's a distributed load putting it into shear of 5 megapascals. And the question is, what are the restrictions that the traction on this face puts on the values of the stress tensor? Restrictions are there on the stress tensor given traction on that face. Remember, these stress tensors, a stress tensor just represents a single point. So these are putting restrictions on the stress tensor just on that face. We don't know what's happening an inch from the face or whatever, but well, the traction vector, you have 20 megapascals in the positive y direction and 5 megapascals in the positive x direction. And that's equal to the stress tensor times the outward facing normal. What's the outward facing normal for this face? Yep, 0, -1, 0. And so I'll put in all the possible values for the stress tensor. So sigma xx, sigma xy, sigma xz. And then symmetry says sigma xy again, sigma yy, and then sigma yz. And then symmetry says xz, yz, and then zz. The outward facing normal is 0, -1, 0. We get 3 equations. Three constraints on the values of the stress tensor. The first one says 5 is equal to, well, let me write it in vector form first. So we have 5, 20, 0 is equal to, what do you get if you multiply this matrix times this vector? You get negative sigma xy, negative sigma yy, and negative sigma yz. And so what we know is sigma xy is equal to -5, sigma yy is equal to -20, and sigma yz is equal to 0. There's still a lot of stuff we don't know, but we know these 3 values. So sigma on that face would be, we still don't know what xx is. We know this one's -5. We still don't know what xz is, but then we know -5, -20, 0, and then sigma xz, 0, sigma zz. And those are boundary conditions then that you can use in your calculations for the values of the stress tensor everywhere. I mean, you can only use those values there, but what you know about the stress tensor on the face is a boundary condition in the sense that it tells you something about what's happening at the boundary of the object. Any questions about that? We're not going to do that in this class, but that's probably the main way that that's useful, that idea. Okay, so now we're done talking about stress. Now we're going to talk about strain. And strain is a measure, stress is a measure of internal loading at a point. Strain is a measure of deformation at a point. We are only going to deal with materials. So materials in this class have a linear relationship between stress and strain. At any point. And that is a version of Hooke's law. When you've seen Hooke's law before, it's been at least mainly related to springs, how far you stretch a spring and the relationship to the force it applies to the things it's touching. But that's a relationship between the loading and the deformation. So with springs, Hooke's law looks like the force is equal to kx, and then the sign, depends on what you're isolating and whatever. For this class, if we're talking about Hookean materials, we're going to see that the stress and, I'll write it as the stress tensor is equal to some matrix M times the strain. So this is a 3x3 matrix. This is a 3x3 matrix. And this is a 3x3x3 matrix. You don't want to deal with those. So we're going to instead represent this as, so we'll do this as a 6x1 vector multiplied by a 6x6 matrix multiplied by a 6x1 vector. But this is the basic idea, and it's the same as Hooke's law. It's just matrices and vectors instead of scalars. One thing to keep in mind is the methods in this class are only relevant for small deformations. So if you ever see a value for strain, that's bigger than about, say, 1 times 10 to the minus third. Well, yeah, let's even say fourth. Anyways, a very small number. That's not like physically meaningful. But I am going to do examples where we're going to get strains bigger than that, just as I demonstrate like how you do these calculations. Okay, but think of that as sort of a cutoff. Real strain values that you do on steel are going to be something times 10 to the minus 6. And if you get values bigger than that, the steel, the metal has moved out of the range where this approach is useful. Okay, so a deformation of a material point. So think of a material point represented by a stress cube. So before the deformation, we have a cube. And after the loading's applied and you have deformation, you'll get a parallelepiped, which is a thing made up of parallelograms. So there are two kinds of changes that happen to the object that you're starting with. There are length changes. Like in this picture, it looks like maybe the length increases this way and decreases this way. Okay, so there's length changes. And then there's also angle changes. If you look at the angle between two of those faces, all these angles start out at 90 degrees. This one becomes more acute. This one over here becomes more obtuse. So normal strains are the length changes. And shear strains are the angle changes. I'm going to start with normal strains. So if we start with, I'll start with a square in the XY plane. And let's say that the initial lengths are, I guess, let's even say this is a rectangle. So I'm going to make these two side lengths different to start with. Let's call this capital L X. That's the length of the side parallel to X. And let's call this one capital L Y. And after deformation, you get, in this case, length along X is increased, the length along Y is decreased. So I'll call this lowercase lx, and this is lowercase ly. Then epsilon xx, that's the normal stress along the x-axis, is equal to the current length after the deformation, the deformed length, minus the initial length, x, divided by lx. Epsilon yy is equal to ly, the deformed length ly, minus the initial length ly, divided by the initial. And epsilon zz is the deformed length lz minus the initial length lz divided by initial. And so with this deformation, something increases in length, sign of that normal stress. Yep. So positive normal stress means you know, it's stretched. Negative normal, I said stress. Negative normal strain means contracted. So the way I drew this example, what would be the sign of the normal strain for x? What would be the sign of epsilon xx? Positive. And what would be the sign of epsilon yy? Negative. And we don't know about z's. Something's happening in z probably, but we don't know. I didn't draw it. Okay, so here's an example. So let's say we start with a material. Let's say this is 8 centimeters. This is 20 centimeters. And after deformation, it shortens along the 20. It lengthens along the 8. I'm going to keep using the same coordinate system. So let's say for this side, the change in length is negative 1 times 10 to the minus 6 meters. And along this direction, the change in length is 2 times 10 to the minus 6 meters. We're going to assume that the strain is uniform throughout this whole shape. Throughout this object. What are the normal strains? Well, if you think about what these definitions of the normal strains mean, if you take the deformed length minus the initial length, that is that delta L. So the XX strain is delta L in the x direction divided by the initial length in the x direction. Along the x direction, the delta L is negative 1 times 10 to the minus 6. The initial length is 20 centimeters or 0.2 meters. We have to get those units the same. And so that is negative 5 times 10 to the minus 6, right? What are the units? It's meters divided by meters, so it's unitless. The strain is just a pure number. And then in the y direction, epsilon yy is the change in the length along the y-axis. divided by the initial length along the y-axis. So that is positive 2 times 10 to the minus 6 divided by 0.8, no, 0.08. And that is 0.25 times 10 to the minus 4. So 0.25. So is that 2.5 times 10 to the minus 3? No, yeah, 5. Then we don't know about z. So notice that strain never has units. And we'll see that's true for shear strain too. A strain is a strain. Any questions about that? Okay. So now we have to talk about shear strains. Shear strains are the changes in angle between faces. And we're going to use angles in radians. So if you start out with a rectangular shape, before the deformation, each of these angles is pi over 2. After the deformation, I'm going to represent this as, so let's say this is the coordinate system. This angle is going to be called theta xy, and that is the angle between the positive x and positive y faces. And defining, being clear about that, those being the positive faces is important, because if I was taking the angle between the positive x face and the negative y face, I would get a different angle. I get the whatever that's called, complement. You had to know that on the SATs once.
No, I didn't.
Huh.
I just got it wrong.
I wasn't talking to you. Yeah, right. So then, based on that definition of theta xy, the other, there's also a theta xz and a theta yz. The shear strain, and I'm going to use the Greek letter gamma for that. Gamma xy is equal to pi over 2 minus theta xy. Gamma xz is equal to pi over 2 minus theta xz, and gamma yz is equal to pi over 2 minus theta yz. And this doesn't make any sense unless you use radians. Okay, so based on this, a positive shear strain is that angle getting more acute or more obtuse? Any other guesses? Yes, more. Very good. So positive means the deformed angle is more acute. Negative means more obtuse. Because so if that angle gets acute between, say, the positive x and positive y faces, then this angle is going to be less than pi over 2, and so you subtract and you get a positive number. Yes? You can do the calculations in degrees if you want, but then you have to convert them to radians for it to work as a strain. And by the way, this is simplified calculation of shear strains. Based on a small angle approximation. So this way of calculating strains isn't even the way you calculate strains if you're dealing with big deformations. You have a more involved calculation to do. I don't remember exactly what the simplification is, but it's not this simple a formula. But this simple formula works perfectly as long as those stay, if you have values that are smaller than 1 times 10 to the minus 4, you can barely, you can't even see that the angles are changing, then these work perfectly well. Here's an example. Let's say that we start out with a material like this, and we're going to use a coordinate system where this is x and this is z. So which direction is the y-axis? It's into the page because y always has to be the... So x cross y has to equal to z. Y always has to be the difficult one. X cross z is equal to negative y. And after deformation, the shape looks like this. And this angle is 1.43 radians. We want to calculate the shear strain XZ. Well, we know that one angle, 1.43. By the way, that's way, way, way too big to be like a physically meaningful strain. I over 2 is like 1.57. So that's way, way bigger than 1 times 10 to the minus 4. But so to calculate this, you're going to take pi over 2 and subtract some angle. But the angle that's given there isn't the angle we want. The angle we want is between the positive x and positive z faces. So we want this one. Right? This is theta xz. And so how do we figure out theta xz? Yeah, theta, so pi is equal to 1.43 plus theta xz. And so theta xz is equal to 1.71. And so gamma xz is equal to pi over 2 minus 1.71, which is negative 0.1392. That's way, way bigger than 1 times 10 to the minus 4. But this is how you do that calculation. If you saw a number like this in something you were doing, like somebody's waiting for the thumbs up on whether to go ahead with this bridge construction, that's a concern for you. Okay? From the 35W bridge? I'm starting to get over it now. Yep. That is the shear strain XZ. Yep. That's right. And this is, well, way, way bigger. You know what I mean. Way, way smaller than negative. So this is not realistic. But we got a negative answer. Does it make sense that we got a negative answer based on whether that becomes more acute or obtuse? Yep. Negative answer means obtuse, and that's what happens to that angle. Okay, so that's the meaning of all of these strains. We're not going to, so this strain that we have defined here is not a tensor. It doesn't have those rotational properties that a tensor has. So we're not going to put it in a 3x3 matrix. Instead, we're going to put it in what's called the Voidform, Void strain. And the way it works, epsilon sub v, the Void strain, is first list the normal strains in exactly the order you would think. So epsilon xx, yy, zz. And then I'm not the one who came up with this format. Maybe there's some mathematical reason that I don't know about. But now you put the shear strains in exactly the opposite order you would think. So the next one is gamma yz, then gamma xz, and then gamma xy. Why? You have to keep. You just have to remind yourself that every time. It's strange, but that's just how it is. Similarly, even though stress is a tensor, it does have the rotational properties of a tensor. We're often going to use Voigt stress, and the organization of that is exactly the same as the strain. So sigma sub v is equal to sigma xx, yy, zz, and then the confuse myself for a second. Okay, so and then this is sigma yz, sigma xz, sigma xy. And a lot of times these shear stresses you'll see written as taus instead of sigmas. So you'll have sigma xx, yy, zz, and then tau yz, tau xz, tau xy. So there's no difference in meaning there. On the other hand, you will sometimes see, I'm not even going to write it down because it's so angering, but you'll sometimes see strain values, shear strains, instead of them being written as gammas, they're written as epsilons. Those have a different meaning. Those are twice as big as these. They just multiply them by 2. Yeah. Well, what can you do? This is called engineering strain, and this is what we're going to use in this class. The other one is the tensor strain. When you are using, there is such a way as to create a strain tensor, but that's not going to matter in this class. And then the last thing I want to write, we'll talk about this next time, is a linear relationship between stress, we're going to talk about the Voigt stress, and the Voigt strain is the Voigt strain is equal to a 6x6 compliance matrix times the Voigt stress. Okay, one more thing. Twist my arm. The Voigt stress, if you want to express it the other way, you can just do it by inverting this matrix. Your calculator will invert this matrix for you, and then you can get that the Voigt stress is equal to a different 6x6 matrix called the stiffness matrix times the Voigt strain. And those two matrices are inverses of each other. Any questions? Okay.